Welcome, everyone, to the Deep Dive. Today, we're embarking on a journey into some truly groundbreaking AI research. We're talking about a paper from, Princeton University and the University of Chicago. It's titled Revolutionizing Reinforcement Learning Framework for Diffusion Large Language Models. And trust me, it sounds like it could really redefine how we think about scaling intelligent models.
Indeed. And, this isn't just some small tweak, like you said. It feels like a fundamental rethinking. The paper introduces something called TracerL.
TracerL, right.
Yeah, a novel trajectory-aware reinforcement learning framework. And it's designed to significantly enhance diffusion language models, or DLMs, especially when they're tackling really complex tasks. The brilliant minds behind this are Yinji Wang, Ling Yang, Bowen Li, Ye Tian, Qi Shen, and Mengdi Wang. Quite a team.
Absolutely. So our mission today is, to really unpack how TracerL dramatically boosts these DLMs' reasoning capabilities, makes them significantly faster.
Which is huge for DLMs.
Exactly. And critically, it provides a robust, accessible, open source framework that the whole AI community, researchers, engineers can leverage right now. We're going to dive deep into not just what they achieved, but how they did it and what it really means for the future of AI development. Okay, so let's maybe try and distill this down for you in a nutshell first. The core problem TracerL is trying to fix is, it's been a persistent one, hasn't it? Diffusion language models, for all their power in areas like image generation, they've really struggled with effective reinforcement learning when it comes to complex reasoning tasks.
Right.
And this seems to be largely because of a significant mismatch between how they're typically trained and the intricate sort of sequential way they actually need to generate coherent text.
And what's truly ingenious here, I think, is that the researchers proposed TracerL. It's this novel trajectory-aware reinforcement learning framework.
Trajectory-aware.
Yeah, and its design is brilliant because it directly aligns the training objective with the model's actual inference process, how it actually thinks step by step. This makes the DLMs not just smarter, but also far more stable and reliable during generation.
And the practical results they're showing are quite remarkable. Using TracerL, they've developed this Tredo series of DLMs. There's a Tredo 4B instruct and a Tredo 8B instruct. And these models consistently outperform even larger, well-known autoregressive models like Qwen 2.57B instruct and Llama 3.18B instruct on some pretty tough math and coding benchmarks. That's a serious challenge to the established players.
And they didn't stop there. They've even gone a step further and created the first long chain of thought diffusion language model called Tredo 8B thinking.
The first COAT ELM, wow.
Yeah. And this model achieved some really impressive gains, like an 18.1% relative accuracy increase on MathH 500 over Qwen 2.57B instruct. But maybe the biggest takeaway here is that it demonstrates diffusion models can actually perform these long, complex reasoning chains.
Which was always seen as the domain of the slower autoregressive models, right?
Exactly.
Yeah.
And like you mentioned, they've released a comprehensive open source framework too, making all this tech accessible for all of us to play with and build upon.
Okay, so stick around because we're going to break down the mechanics of how they pulled this off, why it matters for, every AI researcher and ML engineer listening, and what this potentially seismic shift means for the future of building truly intelligent and efficient AI. So to really appreciate TracerL, maybe we first need to understand the landscape a bit better. What exactly are diffusion language models? We're all familiar with LLMs like GPT, but DLMs have a very distinct flavor, don't they?
They really do. They often operate by projecting discrete tokens into a continuous latent space, or sometimes they use state transition matrices to define a diffusion process. The core idea is iteratively refining some kind of noisy input into coherent text.
It's like denoising an image, but for language.
Precisely. That's a great analogy. Imagine you have a very blurry, static-filled image, and the model's job is to slowly, step by step, remove that noise until a clear picture emerges. In the language domain, that picture is a piece of text.
Okay.
And what's crucial to understand about their inherent advantages is that they allow for potentially massive inference acceleration through parallel generation.
Right. Unlike autoregressive models that generate one token, then the next, then the next.
Exactly. DLMs can, in theory, generate multiple tokens or even whole chunks simultaneously. Plus, they often achieve improved consistency in their output because they leverage bidirectional attention. They can look both forwards and backwards in the sequence context when making decisions.
That parallel generation capability, the ability to churn out parts of a response all at once rather than, word by painstaking word, that sounds like a huge potential differentiator. It promises incredible speed.
It does. But if we connect this to the broader landscape, while DLMs are super promising, especially with that fast parallel decoding potential, they've historically faced this fundamental challenge. How do you effectively apply reinforcement learning to really boost their reasoning capabilities?
And that challenge often comes down to this fundamental mismatch you mentioned earlier, right?
Precisely.
Yeah.
What's been a critical bottleneck, and it's a fascinating challenge, is this mismatch. Imagine you're training a chef.
Sure.
Existing RL methods for these full attention DLMs typically use random masking objectives.
Okay, what does that mean in practice?
It's a bit like teaching a chef by having them randomly chop various ingredients, maybe blindfolded, and then rewarding them if they end up with a pile of perfectly diced vegetables. But when it comes to actually making a dish...
They need a recipe, steps.
Exactly. The chef needs to perform a very specific, sequential, logical series of steps. Peel the onions, sauté them, add spices, then the meat, and so on. The training objective, with its random masking, just doesn't align well with the sequential and logical nature of language generation during actual inference. The skills aren't transferring effectively from training to cooking, so to speak.
Right, so the way they're learning doesn't quite mirror the way they need to perform to generate sensible language. The paper illustrates this point quite well, doesn't it? They talk about Semi-Auto-Regressive Fine-Tuning, or SFT methods.
Yes, they do. And they show that even when these full attention models carried a higher computational load, deliberately aligning the training objective with a more natural left-to-right inference pattern, essentially, training the chef during the step-by-step assembly of the dish significantly improved optimization performance.
If you're following along in the paper, you can see this quite clearly in Table 1. It really underscores how critical this alignment is.
Yeah, that table is pretty telling. You know, block diffusion models, their architecture already breaks things into sequential blocks, so they naturally lend themselves a bit better to semi-auto-regressive fine-tuning.
Makes sense.
But the full attention DLMs, they struggle more to adapt. They often require a more complex process, like slicing the data, to try and achieve that desired alignment, making the mismatch even more pronounced for them under traditional RL methods.
Okay, so here's where it gets really interesting, where the light bulb moment for the researchers must have happened. The paper proposes TracerL, this trajectory-aware reinforcement learning framework. What does trajectory-aware actually mean in this context? Can you paint a clearer picture of how this fundamentally shifts the learning paradigm?
Absolutely. Let's try another analogy. Think of it like training an autonomous race car. Older RL methods might just reward the car if it finishes the race, maybe how fast it finished.
Okay, just the final outcome.
Right. TracerL, being trajectory aware, focuses on rewarding or penalizing the intermediate traces, meaning, every turn the car takes, every acceleration, every decision point during its rollout on the track, not just the final lap time.
Ah, I see. So it's looking at the whole journey.
Precisely. And this is a much more natural fit for how language models actually infer, right? They don't just magically spit out a final answer. They iteratively build on previous context, generating a sequence of tokens. TracerL essentially says, let's reward the process of getting to the right answer, the sequence of steps, not just the answer itself.
That makes a lot of sense.
And the real genius here is that these inference traces, these step-by-step paths, they're naturally produced during the RL rollouts anyway, so they become readily available for learning. You don't need the manual, painstaking effort often needed to collect similar data for traditional supervised fine-tuning. It basically turns a hidden internal process into a learnable signal.
That's a fantastic way to put it. It changes how the model learns, making it not just, better in terms of metrics, but potentially smarter in a way that's far more aligned with the nature of language generation itself.
Exactly.
And what's particularly great, you touched on this, is that TracerL isn't confined to just one type of DLM architecture. The paper highlights its versatility, stating it's applicable across diverse DLM types, including both the full attention ones and the block attention models. That's a huge win for broad adoption and impact across the field, isn't it?
Definitely. It makes the approach much more valuable.
So with this trajectory-aware approach as the foundation, how does TracerL actually achieve its practical efficiency? Let's break down some of the specific innovations they mention. First, there's this concept of a shrinkage parameter S. How does aggregating neighboring steps help reduce training computation complexity and improve efficiency, especially for those notoriously compute-heavy full-attention models?
Yeah, that's a really crucial design choice for making this tractable. The shrinkage parameter S works by effectively coarsening the reward signal. So instead of providing a reward or feedback at every single tiny step in the diffusion or generation process.
Which could be hundreds or thousands of steps.
Exactly, and incredibly noisy and computationally expensive to backpropagate through all those steps. The shrinkage parameter allows the model to aggregate the feedback from S's neighboring steps together. So instead of dealing with, say, T individual steps, you're effectively dealing with S's aggregated steps or chunks.
Okay, so fewer, bigger steps to learn from.
Right. This significantly reduces the number of policy updates required, and consequently the training computation complexity. For full attention models, which already have high memory and compute demands, this is a really clever way to simplify the learning landscape without losing too much fidelity in the overall signal. It's about getting a bigger picture reward for a sequence of smaller actions, making the training much more manageable.
That makes perfect sense. It's like summarizing a long meeting into key action points rather than transcribing every single word. Okay, but then if you're aggregating steps like that, how do they maintain stability? Wouldn't that potentially introduce more variance into the learning signal?
That's a really important question, and it leads directly to the next key component, the diffusion-based value model. This model is absolutely vital for maintaining stability in the face of that potentially coarser growth signal.
So what does the value model do?
It estimates stepwise values. Effectively, it provides a prefix-conditioned, token-wise advantage function. Think of it as a very sophisticated internal critic that can predict the goodness or expected future reward of any partial sequence at any given step in the generation process. This prediction acts as a powerful variance-reducing baseline for the policy optimization.
So it smooths things out.
Exactly. Instead of solely relying on the often noisy rewards you get from just running the model out, Monte Carlo rollouts, the value model provides a much smoother, more stable estimate of the expected future reward from any given state. This is crucial for stabilizing the policy optimization, making the learning process much less erratic. And they demonstrate this compellingly in Figure 6b of the paper. You can see the learning curves become much more consistent.
Got it. So it's about having this smart internal guide to temper the noisiness of the reward signal, allowing the policy model to learn more steadily. And for the block diffusion models, they talk about something called sliced training. How does this formulation maximize the utility of that block attention mechanism for highly parallel and efficient training? And does it cover both the policy and value model training?
Yes, it covers both. So for block diffusion models, the trace generated by their blockwise inference is inherently a sequence of blocks, right?
Yep.
Sliced training is a really brilliant way to leverage this structure. Instead of processing the entire, potentially very long sequence of blocks all at once for every update, the training process selectively focuses on only specific blocks or slices within that trajectory.
So you're not looking at the whole thing every time.
Precisely. Imagine you have a trajectory of B blocks of text generated. Instead of processing all B blocks together for every single gradient update, you cleverly select maybe B different training slices from various points in different trajectories perhaps. This maximizes the utility of the block attention mechanism because each slice only needs to be forwarded through the model once to compute its contribution to the loss and the gradient.
That sounds much more efficient.
It is. It enables highly parallel and efficient training for both the policy model, the one generating the text, and the value model, the critic, ensuring that even with these complex block-wise operations, the computational costs remain manageable. It's really a testament to how they've thought about optimizing every layer of the training stack for this specific architecture.
Okay, so with all that clever engineering in place, the trajectory awareness, the shrinkage, the value model, the slice training, the natural question becomes, how did TracerL actually perform in the real world? Let's transition to those impressive results. Using TracerL, they developed the Tredo series of models. What can these models actually achieve?
Yeah, the benchmark results are truly compelling. And if you're looking at Table 2 and Figure 1, right, in the paper, you'll see the full picture. Let's take TraDo 4B instruct first. It's a 4 billion parameter model.
Relatively small by today's standards.
Relatively, yes. But it consistently outperforms strong autoregressive baselines like Qwen 2.57B instruct, which is a 7 billion parameter model, on various math tasks. For instance, on the challenging Match 500 benchmark, TraDo 4B instruct achieved an accuracy of 75.6%, compared to Qwen 2.57B instruct's 74.0%.
So smaller model, better performance on that specific task.
Exactly. That might seem like a small numerical difference, but in these highly competitive benchmarks, beating a larger, well-regarded model is significant. But the really interesting insight comes when we look at the larger TraDo 8B instruct.
The 8 billion parameter version.
Right. This model achieves significant relative accuracy, gains 6.1% over that same Qwen 2.57B instruct, and a massive 51.3% gain over Llama 3.18B instruct on mathematical reasoning benchmarks overall.
Wow, 51% over Llama 3.18B. That's huge.
It is huge, and it really challenges that long-held assumption that diffusion models would inevitably lag behind autoregressive models in complex reasoning, especially given their unique parallel generation strengths. It also shows strong performance on other tough tasks like ABT 2024 math competition problems and Live Code Bench V2 coding.
That's a phenomenal leap, particularly against models that are often considered, the gold standard for reasoning. And it gets even more exciting, you mentioned this earlier, when they introduced TraDo A/B thinking. This is the first long chain of thought or CoK diffusion language model. How does this particular variant elevate the reasoning game?
Yeah, this model, TraDo A/B thinking, is specifically fine-tuned using TracerL combined with long chain of thought supervised fine-tuning data. And it truly emphasizes strong, multi-step reasoning capabilities. It achieves an impressive 87.4% accuracy on Math 500.
87.4%, that's very high.
It is. And that translates to an 18.1% relative accuracy gain over Qwen 2.57B instruct and a 28.6% gain on the Live Code Bench V2 coding benchmark.
So even better on reasoning tasks.
Exactly. And what makes this particularly groundbreaking for you, the researcher or engineer listening, is that long-code LLMs are known for their power in tackling complex multi-step tasks, right? But they often suffer from prohibitively slow inference times because of their sequential, step-by-step generation nature.
Right. Generating those long chains takes time.
It takes a lot of time. TraDo 8B thinking demonstrates that DLMs, powered by TracerL, can also perform this kind of complex step-by-step reasoning, but with the inherent potential speed advantages of diffusion models. This isn't just about getting better numbers on a benchmark, it's about potentially breaking a fundamental trade-off that exists between reasoning depth and inference speed.
That's a really exciting prospect. And looking at the training dynamics they show in Figure 4, what's particularly encouraging is seeing how both dynamic sampling, which tends to lean towards faster inference, and static sampling, which often prioritizes higher accuracy, steadily improve with Tracer's training.
Right.
This really indicates a strong potential for further scaling and continued performance gains down the line, doesn't it? It suggests the method is robust.
Absolutely. It shows the learning process is stable and heading in the right direction for both speed and accuracy trade-offs. And the ingenuity really shines through when you compare TracerL directly to other RL methods for DLMs. Figure 5 in the paper vividly shows it achieved the best optimization performance.
Better than other approaches.
Yes, even against sophisticated alternatives like using coupled RL objectives or just applying random masking within the blocks. It really underscores the importance of optimizing over the preferred trace, the actual meaningful path the model takes during inference, rather than just some generalized or potentially suboptimal training objective. This specific targeting of the inference trajectory seems to be the key differentiator.
And Tracer broad applicability is a major plus too. You mentioned it works for block and full attention models. The paper shows it's effective not just for math, but also for coding tasks. Figure 6a illustrates this really well, showing that it sets a new state-of-the-art for open-source full-attention DLMs on Live Code Bench V2.
Which is no small feat for those models.
Definitely not. So this isn't some niche solution only for one type of DLM or one type of task. It seems broadly applicable.
And another critical benefit that ripples directly into inference speed and flexibility is TracerL's ability to enable increasing the model's block size. This is highlighted in Table 3.
Why is increasing block size important?
Well, for block diffusion models, a larger block size generally means you can process and generate more tokens in parallel during each step of the inference process. So it's crucial for inference flexibility and acceleration. Being able to train effectively with larger blocks is a big win.
Okay.
And we also see a concrete observed acceleration ratio reported in Table 4. They note a 15.4% speedup specifically on Match 500 dynamic sampling. And interestingly, they attribute this not just to architectural changes, but to increased model confidence.
How does confidence lead to speed up?
Because the model, being more confident thanks to the TracerL training, feels it can safely unmask or generate more tokens per step without making errors. It's more certain of its intermediate decisions along the trajectory.
Ah, that makes sense. Fewer bigger steps because it's more sure of itself.
Exactly.
Yeah.
And they also note the increased average response length, which is further evidence supporting its improved, more detailed reasoning ability. It's not just faster, it's generating more comprehensive outputs.
Okay, so this all sounds incredibly promising. What does this mean for you, the developer or the researcher out there who's listening and thinking, okay, I want to try this out, I want to build on this?
Well, the great news is they've made all of this highly accessible. They've released a truly comprehensive open source framework.
Oh, fantastic. Where can people find it?
You can find the GitHub repository at github.com/gen LLM-RL. We'll put the link in the show notes, of course. But this really lowers the barrier to entry for experimenting with these techniques.
And what does the framework include? Is it just the code for TracerL?
No, it's much more than that. It's quite robust and thoughtfully designed. It supports a whole array of different model architectures.
Like which ones?
Well, pre-trained full-attention models like Eladay and Emanata, adapted full-attention models such as Dream and Diffucoder, and of course the block diffusion models like SDRR and their new TraDo series. So lots of options to start with.
That's great flexibility.
Definitely. And crucially, it integrates accelerated inference techniques right into the framework. Things like KV caching, fast DLLM, which has a tunable window size for attention, and jet engine specifically for block diffusion. And they apply these speedups in both the final inference and during the RL sampling steps in training, which is key for making the training loop efficient in practice.
So the acceleration isn't just an afterthought for deployment.
Exactly. What's more, it includes implementations of diverse post-training methods. So you get various supervised fine-tuning approaches like fully random masking or the semi-AR method we discussed, and several RL approaches including TracerL itself, but also coupled RL and random masking RL for comparison.
Wow, so it's really a full toolkit.
It really is. It's a tremendous resource for anyone looking to dive into DLM research, experiment with these methods, and build upon these advancements.
Okay, so just to recap then. TracerL, with its trajectory-aware approach, seems to fundamentally change how diffusion language models learn, pushing them beyond some of their traditional limitations, particularly in reasoning. It's leading to state-of-the-art performance on complex reasoning tasks like math and code, and also offers significant inference acceleration potential. This isn't just, an incremental improvement. It feels like a potential paradigm shift in how we approach training these powerful models.
I agree. And if we try and connect this to the bigger picture, this work really does present an incredibly exciting research avenue. It's about seamlessly integrating the known accelerated inference strengths of diffusion models.
Their speed potential.
Right, their speed potential, with their now burgeoning potential for strong, even long chain of thought reasoning ability. We know current long-cut LLMs, while powerful, often hit a wall in real-world deployment because their reasoning times are just prohibitive.
They think slowly.
This integration TracerL enables could unlock entirely new opportunities for efficient, scalable, complex reasoning. Maybe even incorporating finer-grained process-level rewards for even stronger supervision down the line. Imagine rewarding the model for how it thinks, step by step.
That's a fascinating idea.
It really raises the important question, doesn't it? How much further can we push DLMs now? Can they truly rival and perhaps even surpass autoregressive models in both intelligence and speed? What new applications will this blend of capabilities unlock for us?
That's a fantastic, really provocative, forward-looking question to ponder. This deep dive into TracerL truly shows the innovative spirit that's driving AI forward, constantly pushing the boundaries of what we thought was possible.
It's moving fast.
It really is. Well, thank you for joining us on this deep dive today. Make sure you check out the full paper. It's dense but rewarding, and definitely explore the comprehensive open source framework on GitHub. You'll find all the links you need in our show notes. Until next time, keep exploring.